Up to now, we've been dealing with the numeric variables, in particular the count of hospital errors. Now we'll switch our attention briefly to categorical variables, which don't have numeric content or may not have numeric content. Could be unordered categories such as fruits, apples, and oranges. They could be ordered categories in which there's a magnitude along which you can rank the categories, such as stage 1, stage 2, stage 3 for illnesses. Could be a binary categorical variable, yes, no, 0, 1 variables. Binary variables actually are among the most common and important types of outcome variables, in the sense that much of decision making in life and outcomes in life can effectively be boiled down to yes, no, or 0, 1 decisions, whether you like or don't like something on a social media site, approve or disapprove of something in a poll, buy or don't buy something, very important to marketers. Jury finds somebody innocent or guilty. A loan could be current or in default. In medicine, doctors track or researchers track survival. And categorical variables are often displayed on bar graphs in which the y-axis indicates the quantity and the x-axis indicates the categories. What we're looking at here is the quantity of applicants to different departments at a university. Note the spaces between the bars, and a histogram, which may look superficially similar to a bar graph but tracks a numeric variable on the x-axis. There'll be no spaces between the bars. In a pie chart, another way of displaying a categorical variable, the circle constitutes the whole, and the size of the wedge indicates the number of the quantity of whatever it is you're tracking, in this case the number of applicants to a school. Now, a pie chart, you're dealing only with situations where you have parts of a whole. A bar graph, the quantities indicated do not have to add up to a 100% or a whole. Another type of graph you'll encounter frequently, particularly in the news media, is the time series graph, where quantity is indicated on the on the y-axis, and the x-axis indicates time. Be careful of small samples with time series. Here we have the U.S. GDP per capita tracked over the years of the recession, both before and after the big recession of 2007-2008, showing a very dramatic initial shift up and then down. A longer time series will generally give a better basis for predicting the future. Here that recession shows up, but as a much smaller relative blip on the long-term trend. We were looking here at GDP numbers, and it's useful to bring in here the concept of indexing, where in this case we're going to account for the effects of inflation. Over on the right you have the inflation index, and we're going to want to adjust the nominal GDP numbers, the actual reported GDP numbers, by the inflation numbers. Just a moment to look at the three different ways we can express inflation. The common one that you'll hear in the news is the percentage inflation rate. Prices went up last year by 3.24%. We can also express this as a price multiplier, 1.0324. That's the amount by which you'd have to multiply last year's prices to come up with this year's prices. And that's related to the inflation rate. You divide by 100 and then add 1. Now, the key information in that price multiplier is contained well out in the decimal range, so it's typically converted to a number in the hundreds by multiplying by 100 to get it to a range more commonly seen and that people can relate to more easily without having to dive down into the decimals. So let's go back to the inflation rate here of 3.24%, translates into an inflation index of 103.24 in the first year and so on for succeeding years. And in the next year, you get 2.9% inflation, which is 106.23 divided by 103.24 as the price multiplier. And to index for inflation, adjust for inflation, to get an inflation-adjusted GDP, you simply divide the nominal GDP, which is the reported actual current dollar GDP, by the inflation index, and that gives you inflation-adjusted GDP. Economic data is often indexed. So are web statistics. Here you have Google Trends for two terms, data science versus predictive analytics. This is the quantity of searches, but actually it's not the actual number of searches, but rather for the entire multi-year period here, Google has found what period had the most searches for either term, and then they've set that to 100. They've divided it effectively so that the top number of searches comes out to be 100, and all the other data points in the charts, both charts, are the relative value to that 100 maximum. Indexing is a transformation of the data to make comparisons easier, either over time, as with GDP indexing, or in comparison with other variables, as we saw with the indexing of web searches. And a similar similar purpose is served by normalization or standardization of the data, where we divide by the standard deviation and subtract the mean. We'll see that in the next section.